So remember that Ptolemy's model was able to predict the locations of the planets accurately enough, in fact. And it actually matched current observations of that time period also accurately enough. But it carried in its midst a physical impossibility, which is having these different shells, these crystalline spheres, orbit in the sky about a point that's off-center, known as the equant. And as I said, Ptolemy realized that this mistake, this physical impossibility, would have to be corrected by future astronomers. And so when the Muslims translated all the work of the ancient Greeks, they immediately recognized this problem and they set out to try to fix it. And so there were many different attempts to do that. And as I said, one astronomer builds on the work of the ones that came before them. And the first correction that we actually see to this physical problem comes at the hands of a Persian astronomer known as Nasir ad-Din al-Tusi. Now, Nasir ad-Din al-Tusi was actually working at one time at a fortress known as the Alamut Fortress, which was a castle or fortress on top of a hill in northern Iran today, northern Persia at the time. He was such a famous astronomer that his fame reached as far as China and the regions where the Mongols lived. He also lived in that time period when the Mongols were actually sweeping westward. And so the army of Hulagu arrives at Alamut Castle, this fortress on top of the hill in Persia, knowing that al-Tusi was there, and the soldiers were given command that when they find Tusi, they actually needed to preserve his life and all his books. And that's because the Mongols actually believed in astrological predictions. They needed these astronomers who were so known and famous to be able to help them make predictions, especially military predictions. When is a good time to invade this place or that place? And in fact, it was actually one such time that the invasion of the Mongols into Baghdad and the fall of Baghdad in the mid 1200s happened at such astrological predictions. And in fact, I think it was in that time period that al-Tusi was not very popular in Baghdad because the sacking and the burning of Baghdad and also the drowning of all the books, the hundreds of thousands of books in the libraries, happened at the hands of the Mongols based on these astrological predictions by Tusi. Nonetheless, he was a famed astronomer, and during that time period when they actually snatched him from that part of Persia, the Mongols actually went to build their Ilkhanate dynasty, or their basically kingdom, if you may call it that, in Moraga. They made Moraga actually the capital of the Ilkhanate at the time, and Moraga was in current-day Azerbaijan. And that's actually where al-Tusi realized that he can take advantage of being such an important astronomer to tell, because he really ached for a new observational table that would have current observations. And so he told the Mongols, he told Hulagu, that he needed to build a new observatory. And that's because he actually needed to update his records of the planets and the stars, and so he can give Hulagu more accurate astrological predictions. And of course, the Mongols really wanted to do that. And for the first time in the history of Islam, it was actually Islamic money that was paid by Muslims for charity and almsgiving and all of that. That part of that money, for the first time in the history of Islam, was actually allocated to build an astronomical observatory, which is very important to note in the history of observatories, that now they actually had a resource, a money resource, to be able to fund such a building. And that's why the Moraga Observatory was able to be built with basically a large observatory with large observational instruments that can make the most up-to-date, accurate observations at the time, and it was all headed by al-Tusi. In fact, the Moraga Observatory was very important in another aspect because it actually attracted astronomers from around the globe at the time who could arrive here. And so the Mongols brought with them the Chinese astronomer Fao Mungi, and al-Tusi himself came from Persia. He was the head of the observatory. He recruited one who's known as al-Maghribi, the Moroccan, basically indicating where his native origin would have been. He also recruited al-Urdi, who came from Damascus, Syria, and Shirazi, who came from another region in Iran, among many. So it was really an international, the very first known international observatory, and a lot of important work actually happened there. However, if we go back to Ptolemy's model and that problematic error that Ptolemy recognized from the get-go, spheres that can't orbit about points that are off their centers, Tusi was aware of this problem, and being the genius mathematician that he was, building on works of those who came before him, he invented another mathematical tool that he superimposed on Ptolemy's model that fixed that physical impossibility of spheres rotating about points off center, or point known as the equant. Here is what al-Tusi did. He created what became known as the Tusi couple. And the Tusi couple basically is having two circles that are coupled together, as you can see in this diagram. And when these two circles moved in a certain fashion, they allowed for the planet, so this would be the red planet, to move along a straight line back and forth along that straight line. So you can see the planet moving along the straight line and back up. And you might say, well, why do we need this kind of motion? Remember, it was very important to be able to create the motion where the planet could get closer to Earth. So if Earth is even further down, that the planet, let's say Mars, would sometimes get closer to Earth, hence becoming brighter, like here, and sometimes going further away where it actually becomes dimmer. Let me tell you in a nutshell what the Tusi couple is, and then we'll watch an animation. So what al-Tusi said is he coupled these two circles. Remember, these are mathematical circles, so they're not necessarily actual, but this kind of motion would create the apparent motion of the planet and preserve the retrograde motion. So it also keeps the retrograde motion according to this mathematical model. So if the pink circle rotated in one direction twice as fast as the blue circle rotated in the opposite direction, it would actually allow the planet to move along this straight line. So let's actually, let me demonstrate that with one part of the motion, and then we'll go to the animation. If this pink circle rotated counterclockwise by half a circle, so only half of it rotated counterclockwise, and at the same time the blue circle rotated clockwise a quarter of its circle, then this planet would have moved all the way to this location in the center. And of course, if it does that 4 times, the pink circle rotating around by half a circle while the blue by a quarter circle in the opposite direction, it would move the planet down this way, then back up to the center, then back up here. Let's take a look at this animation that shows us this motion. So as the inside circle that's coupled with the bigger circle moves twice as fast, so as it moves around twice as fast as this opposite one moves around half as fast, it would allow the planet to keep moving back and forth along a straight line. So if planet Earth, let's say, is somewhere here on the left, sometimes the red planet gets closer and sometimes further. And that's actually the motion that al-Tusi created to be able to fix the equant problem by Ptolemy. So remember, Ptolemy said the equant is the point about which these spheres rotated. And here's how, if we take Tusi's couple and superimpose it on this Ptolemaic model, we get the following. I actually used an illustration from Kennedy's paper, E.S. Kennedy's paper, which is titled Late Medieval Planetary Theory, which is a really neat paper to go back and read if you're interested in a more in-depth understanding about this model. And so this hashed circle, the hashed line, represents Ptolemy's old deferent. So remember that deferent was able to very well predict basically the positioning of the planets relative to the observations. So it was very accurate. The only problem was that this dotted line was centered about the equant point, which is off center. That was the problem. And Tusi said, well, now we have actually a remedy for this. He mathematically provided a proof for this Tusi couple. And that's what every mathematician would do when they come up with a new theorem. And so here's how al-Tusi superimposed his couple, so these two circles that are coupled, onto Ptolemy's model. He said, first of all, these two circles that are coupled, the big one is carrying or allowing the small one to roll inside of it. But the big one is the one that goes around on the deferent. He said, let's make the center of the big circle of the couple, have its center go around another circle, and this circle, as this circle moved around, this is the new deferent that Tusi actually came up with. He said, let's create a new deferent. This new deferent, which is the solid big circle, is actually centered on the equant. So the equant doesn't go away, but now it becomes a point that is a center of a sphere. If this actual sphere, this solid circle, was made by a sphere, and this actual sphere was rotating in the heavens, it actually rotates about the equant point. And that's what was important. That's what Ptolemy wanted to do, but he actually died before he could come up with a model that can actually allow the equant point to be the center. And now we have the Tusi couple. You have a circle that's centered upon another circle that also rotates about its own center. As the Tusi couple circles move around, the planet that I'm actually showing in red ink, as this inner circle moves to the left, you can see how it actually rises going to the left or going clockwise. This small circle moves to the left, rolls around the bigger circle. As the bigger circle rotates to the right or rotates counterclockwise. And as it does so, this smaller circle rotates twice as fast as the bigger one. And as it does so, it allows the planet to move along the line that connects basically from the equant all the way back and forth. But that's not as important as it actually produces the same locations of the planet as Ptolemy's model, which, remember, matched observations really well. Sometimes the planet would be really close to Earth along that line. Remember the line that is the diagonal or the diameter of the circle of Tusi's couple. Sometimes the planet ended up being closer to planet Earth, so being at perigee, as we say in astronomy. Hence the planet would be really bright. And sometimes the planet would end up further away from Earth on the other side, or at apogee, as we say in astronomy, allowing the planet to look dimmer to an observer standing on Earth. So Tusi's couple resolves the issue of spheres rotating about points off center. Everything in Tusi's circles, everything in Tusi's model, which is all the solid circles in here, all of the solid circles all rotate about their own physical centers, and that is physically possible, just like the basketball.